So good afternoon, everyone. I am Adyasha Sahoo from IIT Roorkee, and we will be discussing today the contents of week 10 for our Power System Engineering course. So this week 10 we will be mainly discussing regarding the topic of load frequency control. So can you tell me what are the two states of the power system? Like which quantities are called as the state of our power system? Can you guess it? So that is basically your frequency of the system and the voltage. So by voltage, basically I mean the voltage magnitude that we get during solving our load flow studies. And for frequency, it is related to the angle of the voltage delta that you basically solve in load flow studies, right? So our aim is for the smooth operation of our power system that these two states should always be within the limits, right? So for smooth operation of our power system, so frequency and the voltage need to be maintained within a specified, or we say allowable range. So the frequency, in India it is 50 hertz. So it is allowed that the frequency can be varied between 49.5 hertz to 50.5 hertz. And similarly for the voltage, it can vary between zero point 0.9 or 0.95 per unit to 1.1 or 1.05 in per unit. So if the voltage or the frequency is beyond this range, like below the minimum range or above the maximum allowable range, then the certain hampering of the system will happen basically. So for that, we always want the frequency and voltage of our system to be maintained within this range. So for this week, we'll study how this frequency is basically maintained at a fixed or within this range for our power system. We are not considering the voltage in this week here. So, in our power system, the load is continuously varying, right? The load is never fixed. Load is continuously varying. And once the load is varying means we have to change our generation accordingly to match this varying load. If we don't do that, then what will happen? It will lead to frequency violations. So the generation should match or follow the load, right? But the challenge is, let's say you have a steam generator, thermal generator, or a hydro generator. It cannot instantaneously increase its output, right? Let's say if the generator is operating at 10 megawatt power output now, and you the load, let's say it increased by 5 megawatts. So it will generation will have to increase to 15 megawatts, right? but it will not be instantaneously. It will gradually move from 10 to 15. And why it is so? Because these are machines, right? So for increasing the power output of a thermal generator, what you need to do? You need to burn more coal so that more steam is formed, and that high pressure steam will lead to increased output. And similarly, for hydro, what you have to do, you have to open the gates so that more water flows into the blades of the turbine, and that turbine will then give more power output to the shaft of the generator. So during this process, let's say the heating of the coal or opening of the gates in a hydropower plant, so that will take certain time. So that the transient time will be there. So how that will be done, that will be decided by the controller. Basically, we have, like I said, we have frequency and voltage. So the frequency is basically controlled with the help of your active power. If you remember the decoupled equations of the power system, so we have seen that the change in frequency is majorly affected by the change in active power, and the change in voltage magnitude is basically affected by the change in reactive power. So this is due to the decoupled nature of power system. So what we try to do, we try to match the frequency by varying the active power, and we try to maintain the voltage profile using the reactive power. So for that, what we have in a generator is basically, let's say this is your, you have some valve or gate control mechanism to open the valves of the steam or gates of the hydro generator. So how to open or close this valve? So that you will know from the load frequency controller. So the load frequency controller, it will do some computation that we will see, and it will give us the output that how much amount of gate or how much number of gates or valves are to be opened in the current condition. And this load frequency controller, basically you give the information of the change in the load or the change in the tie line power in case of your multi-area system, and you also give the change in frequency delta f. So you have frequency sensors who will basically sense the frequency of the system every second, and they will how this delta f will be basically your nominal frequency minus your nominal or your reference frequency minus the current frequency f of the system, and this current frequency f will be the frequency at the generator that will be measured using this sensor. So I have a valve here, and the output of the valve is will be connected to the turbine, right? So that more steam or hydro will come in contact with this turbine to rotate it, and this output of the turbine will rotate the shaft, and this shaft is the mechanical input to your generator, so that your generator will give you electrical output, right? So let us consider a three-phase electrical output here. So this is your generated power, active and reactive. So this part is for the active control, active power or frequency control loop. And similarly, it will have a voltage sensor for the reactive power or the voltage control loop. So similarly, here you will monitor the voltage through the voltage sensor, and that is given to your automatic voltage regulator or your AVR, and that is controlled using the field excitation of the generator. Like the frequency is controlled to the valves or gates of the generator. The voltage is controlled to the excitation or the generator field. So this is your excitation system. And let me draw it near to the field of the generator. So the generator field is here, and here we have the excitation system. Right. So this is how the we control the active and reactive power to in order to control the frequency and voltage in the system. So in this week we will be mostly considered with the active power and frequency control. The voltage and excitation part is not covered here. So if we see the model of a generator supplying a single load, so generator or isolated generator supplying a load. So we see that the steam or water, so that is controlled using the opening of the valve or gate so that it reaches the turbine, and the output of the turbine to the shaft is connected to the generator, and the generator will then supply it to the load. And here we have the governor who will sense this output, always this frequency here, and control the opening and closing of this valves. So this is known as a isochronous governor. So next, this isochronous governor means, usually it means a constant. Isochronous means constant speed. So it adjusts the opening of the turbine valve or gate to maintain the system in its nominal value. So if we see the block diagram of that isochronous governor, so it is basically that the steam, this is your valve, turbine, generator, then your load. So here you're giving the mechanical input to the generator and getting the electrical output like it was here. So if this is the mechanical torque, then this is your electrical torque. Similarly, here also. And this will be used to compute the change in frequency with respect to the reference. How we will do that? We'll give a reference frequency to this. F reference, and the frequency of the system, let that be currently F. So we compute the delta F. So this delta F is basically your current system frequency minus your reference frequency. So that reference can be 50 hertz or 60 hertz or whatever you feed to this. So if this delta F is not 0, then this control isochronous governor will try to bring back the delta F to 0. So by keeping this, the aim of the governor is to make delta F 0 so that your frequency is always equal to the nominal or the reference frequency. So that is done with the help of your PI controller. So the delta F will be passed through a proportional, that PI is proportional plus integral, right? So a gain of minus K, and then we have a integrator. So the integrator we represent by 1 by S in Laplacian domain, and that will be used to operate your valve or gate. So that we call as delta E. So that decides your valve position. So if this delta F is greater than 0, which means that your current frequency is greater than your reference frequency. So what we need to do here, do we need to increase the generation or decrease the generation? If the frequency is greater than the reference frequency, we need to decrease the generation, right? PG need to be reduced. So it will give the delta E to close the valve. Not all, some. According that how much quantity will be given by this isochronous governor. And similarly, if delta F is less than 0, which means that your F is less than the reference frequency, that means you need to increase the output of the generator. So it will give the signal to open the gates or the valve to maintain the frequency equal to the reference frequency always. So that was your isochronous governor. But what is the problem with this isochronous governor is basically the drawback of isochronous governor. So it will work perfectly fine if we have a single generator. There can be multiple loads, but if we have only one generator supplying all those loads, then the isochronous governor will work fine to maintain the frequency at equal to the reference frequency. But if we have two or more generators in parallel in an area supplying to the load, so what will happen is basically this F reference that we set. So F reference for each generator, that is in the case for in case of two or more generators supplying the load. Then the F reference for each generator cannot be exactly same. So because that setting that we do, we cannot keep it exactly same for all the generators. There will be certain mismatch in this reference frequency for each generator. So what will happen is each generator will try to bring the system frequency F, system frequency that is F, to its own reference frequency. So what this means that, let's say you have two generators G1 and G2 with frequency reference frequency FR1 and FR2. So what will happen? This PI controller that you have for generator 1, it will try to bring the delta F, that is your F minus FR1 to 0, or it will try to bring the pull the system frequency to reference FR1. Similarly, for the second generator, this delta F, it will try to bring the system frequency near to its reference, that is FR2. So there will be, so the generator will fight with each other here. Fight to bring F to FR1 or FR2, or if there are other generators similarly to their own reference value. So hence, in those cases, the isochronous governor will not work. So for that, what we do next is we will study the governor with a feedback loop. So what we do, we have this right with the governor, then we will add a feedback loop here. So I'll draw it once again. So basically the governor characteristics or diagram will be same only. Valve, turbine, generator. Fr is minus, this is plus. Then K, then your integral, and that was your delta E. So now one feedback from delta E will come, right? So this is your governor with steady state feedback. So if we reduce this part, this block diagram here, So that will be again that will become delta F, that will pass through P, then I, and that is your delta E. And again from delta E, you have R, that is minus, and earlier it was minus K, so we will bring that minus here. So that is again reduced that single loop to a one path, then it will just be delta F minus 1 by R, and this will be 1 by 1 plus STG, and its output is delta E. So that is your reduced block diagram. So R is your droop here, droop or your speed regulation parameter we say, and your TG is your governor time constant, and its value is 1 by K times R. So what is this droop or speed regulation parameter? We'll see. So this droop coefficient R, so it is basically determines the change in frequency or steady state frequency versus the load characteristics of the generator. So basically it is so this is frequency in hertz versus the output power of the generator. You can say PG. So it looks like this, right? So this at this point, what is your load on the generator? It is generating zero, right? Or no load. So the frequency here is known as your F no load because here the power generated is F no P no load, right? Or zero if we say the losses are not there. Similarly, at this point, so the power is maximum or the rated power of the machine, right? So in per unit, maximum or 1, or that is your full load or maximum load. This is your F full load. So the drop in frequency from no load to full load for the increase in power output from no load to full load, that is your R. So R is basically the drop in frequency or change in frequency with respect to the change in output power of the generating unit. So basically, if let's say the current system frequency was F naught, yes. So let's say if the current frequency was F naught, then the generated power will be this P1. And if say there is a change in load, that means the power has to increase from P1 to P2, then the frequency will drop from F naught to F. So this is your change in frequency delta F, and this is your change in power delta P. Right. So this R is basically, you can say, percent change in frequency with respect to percent change in output power. That is your group coefficient R. So if a group is given as let's say 5%, it means that the frequency will drop from, and if the let's say nominal was F some no load, so F no load to full load, there will be a drop of 5% when the output of the generator increases from 0 to maximum. That is your 1 per unit, right? So that is the interpretation of droop. Now let's see how this works when we have more than one generator. So let's say we have two generators operating in parallel and sharing a load. So how this droop works, we'll see. So load sharing by generators in parallel. So let's say we have two generators with two different droop characteristics. So this is, let's say, first one, and the second one. So this is your F, this is your P. So R is your delta F by delta P, which means basically the slope of this line. So can you tell me which of this following has greater droop? Like R1 is greater than R2 or R1 is less than R2? Which one is correct looking at these two characteristics? Let me draw it more flat. Can you tell me the slope of the line only, right? So which line is having more slope? The first one, right? So this is the relation, right? Here, first one is having greater slope than second one. You can see the slope of the line. It is more. So how we decide that? We see the angle it makes with the yeah. So just we'll keep this in mind that R1 is greater than R2 here. Okay. So let's say initially they are operating at certain point F naught, and the load shared by them is, let's say, P1 and P2. So let's say this is in steady state, and let's say there is a increase in load. So increase in load means the generation has to increase. So in what proportion? Let's say there is a 100 megawatt increase in load. So how this 100 megawatt will be shared by these two generators? Will they share equally, or this will first generator will share less load or more load? That we will see. That will be governed by its two characteristics. So basically, there will be increase in the output of both the generators to meet the increased load demand. So let's say the increase is P2 dash and P1 dash, and the new system frequency is F. So what is the change in output of generator 1? It is P1 dash minus P1. And how much was change in output of P2? It was P2 dash minus P2. And this delta P1 plus delta P2 is your change in load, delta PL, which I was telling is 100. And from the Droop relation, we know also this delta P1 will be, see, R is delta F by delta P here, right? So delta P is delta F by R. So delta F by R1, here delta P2 is delta F by R2. So if we divide these two equations, what we will get? Delta P1 by delta P2 will be R2 by R1. That means the amount of load picked up by the generator is inversely proportional to the droop. What it means that the generator with greater droop coefficient will pick less amount of load. That means, firstly, we had remembered the relation between R1 and R2. R1 was greater than R2, which means that the amount of load picked up by the generator 2 will be more than generator 1, because here we see it is inversely proportional, right? And that you can see from this diagram also. You see delta P2 looks greater than delta P1. Then how to basically control. Next we'll see governor with by changing basically the load reference set point, we can adjust the frequency load relation. Basically, to this loop here, what we'll do, we will give another set point here, U, and by wiring this load reference set point, we can control the frequency load relation. Right. So that we'll see in the questions how. And after that, governor modeling. So this was first we saw isochronous governor. To that, we added the feedback, that is your droop R for two or more generators, and then after that, uh, we saw that we can also add the load reference set point. Okay, so this covered the governor modeling. The next part is your turbine modeling, right? So till now we studied only this lower governor modeling part. Now we'll see the turbine modeling. So there are not much questions for this turbine modeling. It is just some derivations. And for the turbine modeling, if you remember, basically there are three time constants, your TT, TR, and TC. So TT was due to the steam chest. This was due to your inlet piping. Sorry, this was due to your reheaters. And this was due to your crossover piping. So these are basically representing the time delays due to this steam chest or reheaters or crossover pipings. And using this, we basically this time constant, we are modeling the turbine. So for the turbine modeling, what you will get is basically something like after the derivations, you will get as delta Pg by delta E was 1 plus S Kr Tr divided by 1 plus STT plus STR. Right. So that we'll not see in detail, that is covered. So now let us see how this change in basically delta Pg minus PL is accounted. So we see that it is accounted in two ways. So firstly is the rate of increase of kinetic energy stored in the rotor of the generator. So let's say at the nominal frequency F naught, the stored kinetic energy was WKE naught, and it was H times your PR in megawatt second. So H is your inertia constant and PR is your rated capacity of the generator. So this is basically megawatt and this is inertia constant in second. So that is your WKE naught. And basically, so the kinetic energy is proportional to the square of the speed, right? So kinetic energy is directly proportional to your omega square, right? Half I omega square. And you know omega is directly proportional to F. Omega is 2 pi F. So we can say kinetic energy is also directly proportional to frequency square. So kinetic, yes. So now let's say new kinetic energy at frequency F naught plus delta F. We need to find out. So what it will be? So WKE1 by WKE naught will be F naught plus delta F square divided by F naught square. So that gives WKE1 as F naught square plus delta F square plus 2 delta F naught divided by F naught square multiplied by WKE naught. So this we can neglect, it will be delta F is small and delta F square will be further small. So neglecting that term, we get WKE1 as 1 plus 2 delta F by F naught into, instead of WK naught, I can write as inertia constant times the rated power PR. So the rate of change of kinetic energy, so HPR will be constant. So we'll get it as 2 HPR by F naught d delta F by dt. So that is your first component of that. After that, we'll see the second interpretation account. So next we consider that second one, that your change in load is sensitive to frequency. That is, whenever the frequency changes, we consider that the load will also change. It will not remain constant. So that can be expressed as change in load with respect to change in frequency. We denote it by the parameter D. So for delta F change in frequency, the load change will be, that is delta PL will be this delta PL into delta PF multiplied by change in frequency. So that is basically D times your delta F. So if we combine this kinetic energy and load sensitive frequency, then we'll get the combined expression. So this delta Pg minus delta PL. So first is your change in kinetic energy, F naught d delta F by dt, plus load sensitive to frequencies d times delta F. So if we divide that by the rated power, that is PR, so delta PL by PR, we get 2H by F naught d delta F by dt plus dPR delta F. So basically these quantities are then converted to their per unit values, right? So delta Pg in per unit, delta PL in per unit, 2HF naught d delta F by dt plus d in per unit in delta F. But delta F is actual, it is in hertz, it is not in per unit, right? So if we take the Laplace here, before that, if I do this here, I will get delta F as delta Pg minus delta PL divided by this term D plus 2HF naught, and this one will be S. So from this I can write delta F as delta Pg minus delta PL into Kp by 1 plus STP. So if you just compare this one and this expression, so you get Tp, which is your power system time constant, as 2HdF naught, and Kp is your gain of power system, which is your 1 by D. So finally, for the generator load model, the block diagram is so delta Pg minus delta PL is your Kp 1 plus STP times change in frequency delta F. So if you remember, first we had the governor model. To that we then added the turbine model, and finally we had the rotor and load model. So that gives the complete block diagram of the generator unit with turbine and governor. Okay, so now let us solve the questions. The first is the dimension of load damping parameter D, which indicates frequency sensitivity of load in load frequency control of power system is. So what will be the answer? Can you tell first? So what was D? D is change in load with change in frequency, right? So what is the dimension of this power? At the end it is power, right? Power is work done per time. And what is work done? That is force into displacement divided by time. So now just can you say, basically M is here mass, L is length, T is time. So force is mass times acceleration, right? So mass means M, acceleration is meter per second square. So length second t to the power minus 2. And what is your displacement? What will be it? That is just your meter, right? Yes, and time is t. So I will get that as m L square t minus 3. So here I got m L square t minus 3. And what will be delta F? F is hertz, right? So that is 1 by T, which means it will be T minus 1. That will give me as M L square T minus 2. So which is your option? B. Okay. Now next question. So for modeling of a typical three-phase balanced power system, the time constant of speed governor, turbine, and power system have to be chosen from the four given time constant THD, TT, and T power system. So which one will be sufficiently accurate choice for T power system? So here, if you remember during the derivations also, the governor time constant was the smallest, right? So that's why we neglected that governor time constant there in the lectures, if you remind. So that is in the order of 0.8, something like that. Then after that, your turbine. So it is around zero point 0.3 to 0.5 second. And for the power system, so T power system was nothing but your 2H F naught by D, right? And that is in the order of your 10 to 15 or 15 to 20 seconds. So you can see that your T power system is much greater than your turbine and governor. And so you get this relation here. So which one we can choose for T power system accordingly here, which is the greatest among these, right? So this one can be for the governor, T4 can be governor, T3 and T1 they can be your turbine models, but T3 that is 0.45 second, so that will be your power system, right? So T4 can be governor, your T1, T3 can be turbine, and T2 can be your power system, that is T2. Okay. So now next question is objective of AGC. So the objective of AGC is to hold system frequency at or very close to a specified nominal value, to maintain correct value of power exchange between control areas, or to maintain each unit generation at the most economic value. So basically, let me insert a slide here. So this question is regarding the hierarchical control that we say basically. So in that we have primary control layer, secondary control layer, and lastly we have tertiary control layer. So the primary control layer, it is the fastest. So that is similar to your group. So whenever there is a disturbance in the system, so the first reaction will be from the primary control layer, which is the first one, and it is the fastest. That is, it will operate in the order of millisecond to seconds. So its responsibility is to hold the system frequency, this one. So that is the function of your primary layer. Then second, in an interconnected power system comes the, this is the fastest, we can say this is somewhat fast. So that is for the control of this tie line power flow between two areas. Let's say this is area 1 and this is area 2, and they are being connected with this tie line. So it basically controls the power flow in this tie line to maintain the frequency in this area 1 or area 2. So let's say if there is a drop in frequency here, which means that it needs additional generation. So if delta F1 is dropping, what we can do, this delta Pg2 can increase. So the delta P tie line, just a second. Yeah. Yes, so I was saying that if delta F1, that is frequency in the area 1 falls, that means the area 2 can help here by increasing its generation, so that your P, what will be the direction of power flow of the tie line? Will it be from area 1 to 2 or area 2 to 1? If the frequency in area 1 is dropping, then which one is correct? So frequency in area 1 is falling, that means area 1 has deficit power, right? It requires additional power, and that will flow from area 2 to 1. So this will be the direction of power flow in the tie line. So that is done with this area control error that we'll see in the coming session basically. So its operating time is within seconds. And lastly, so if you see, so this is your function of your secondary layer to maintain the correct value of power exchange between control errors. That is done using your minimizing this area control error. We'll see it in the next one. And finally, the tertiary one. So this is the slowest. So it occurs in minutes. Like so that is the slowest one, slowest control layer. So it looks after the economics, right? Like which there will be, let's say, another in a very large control area. Let's say for secondary area, we had simpler with two interconnected system. Let's say we have a huge power system like India. So let's say there is a drop in frequency here. So then power we can get from area this one, two, three, or four. But which one will be most economical? That is, which one will be cheapest or which one will be having less cost. So that will be decided using this your tertiary control layer, or that we say your AGC. So its aim is to determine the most economical, you can say, action to be taken to correct the frequency. So that is your tertiary layer. This is your AGC to maintain each unit of generation at the most economic value. So from here, I can say that this only three is the objective of AGC. Is it clear? So no, basically it is the combination of all three. So AGC is this complete process. So AGC is this your primary plus secondary plus your tertiary layer. So that as a whole is called your automatic generation control. So that is 1, 2, and 3. Now the next question. So a 10 MVA 50 Hz alternator is operating on full load at unity power factor. So a load of 1 megawatt is suddenly applied. So change in load is 1 megawatt to the machine, and the steam valves to the turbine commence to open after 0.45 second due to time lag in governor system. So assuming inertia constant of 2.5 kilowatt second per kVA, calculate frequency just before steam valve begins to open. So this is the question for your kinetic energy. So first we will find the initial kinetic energy, right? So that will be your inertia constant times machine, right? PR that we say, right? So this is your PR times H. PR times H. So 10 is the machine rated capacity, 2.5 is the inertia constant. So that will give us 25, and this is energy in megajoules. So we had seen that relation where change that was proportional to the square of frequency, right? This one, right? Into WKE naught. So what will be the change in kinetic energy after the increase in load? So change in kinetic energy after load increase. So that will be 1 megawatt is the change in load, right? So 1 megawatt, and the time that is given as 0.45 constant here, right? So 0.45, that will give us 0.45 megajoules. So from here I can calculate, this one is known, this one is known, F naught is known, 50 hertz initially, so I can calculate F. So what will be F? F will be WK1 by WK naught square root into F naught. So that is your square root of, what is WK1? It is initial minus change we have computed as 0.45 divided by initial was 25 into 50. So that will get as 49.54795 hertz. So that is your option A. The next question. So a power system has two synchronous generators and their governor turbine characteristics are given P1 and P2. So assume that the generators and transmitters are lossless. So no load frequency of generator 2 is asked here. So here if you see, basically F no load of generator 2 is asked here. So that we can get by, when it is no load means what is P no load 2? This point, right? That means 0. So in this equation P no load 2 is 560 times F no load 2. So this is 0. It's 560 minus F no load 2. So F no load 2 is 60 hertz. And here it is asked in radian per second. So omega you can calculate as 2 pi F. So that will get as 376.9911 radian per second. Right? So that is option D. Similarly, can you calculate F no load 1? What it will be? What will be F no load 1? For machine 1, what it will be? So in this equation, you need to put P1 as 0, right? Then what you'll get? That will be also 60 hertz, right? So that means that their starting points are same, although their root can be different. So this will be their characteristics, frequency versus power. So the same question here, find out the percentage load shared by generator 1 if the total load is 1 megawatt. So if you remember here this one, so this is the question here, right? Your root equation, the equation of this line is basically given in those questions, and you need to find the this P1, P2. So basically, so let's say they are operating at this point. So this PP1, this PP2, and this be your system frequency F. So it is said that the total load is 1 megawatt. So P1 plus P2 is 1 megawatt. And what is P1? P1 is so P1 is 100 into 60 minus F plus P2 is 500 into 60 minus F. So here you see P1 and P2 are in kilowatt. So we'll keep this load also in kilowatts. So this will be 1000. 1 megawatt is 1000 kilowatt, right? So from here, what I'll get 60 minus F plus 300 minus 5F equals to 10. So F is 350 by 6. So that is coming out to be 58.33 hertz. Now once you know the F, so can you calculate percentage load shared by generator 1? So you know F, so what will be P1? P1 will be 100 into 60 minus F. So that will give 166.66 kilowatt. So what will be the percentage load shared? That will be P1 by total load, right? PL, that was 100,000 kilowatts. So 166.6 divided by 1000 into 100. So that will be around 16.66%, right? So that is option A. Now, so 50 hertz small system consisting of 5 identical 400 kVA generating units feeding a total of 1500 kilowatt. So inertia constant is given and the total load varies by 1.25% for 0.5% change in frequency. That means it is information for D. So when there is a sudden increase in load by 100 kilowatt, find steady state frequency, assuming there is no speed governing action. So that means all will be only for D. So first here it is given that 5 identical 400 kVA units, which means that your base MVA is number of generating units is 5 into 400 is each rating. So that will give us 20 MVA, 2 MVA, not 20. Okay, now from here I can calculate first D. So D is change in load by change in frequency. So initially the load is 1500 kilowatt. So in megawatt I can write as 1.5 plus what is the change in load, that is 100 kilowatt. So 100 kilowatt or zero point 0.1 megawatt. So I can write this, let this PD naught plus delta PD and it is given that it is varying by 1.25%, right? And what is the change in frequency? It is 0.5 in 50 on 50 hertz base, right? So for this much change in frequency, that is 0.5 into 50, the change in load is 1.25 times. Agreed. So this part is actual change in load and this is due to the load sensitive to frequency, right? So I can get PD naught as 1500 or 1.5 plus 0.1 change in frequency is 0.5% and the load change is 1.25%. So that will give us 0.08 megawatt per hertz, right? Now if I do it in per unit, D in per unit, That will be 0.08 divided by 2 megawatt per unit per hertz. That is 0.04 per unit megawatt per hertz. That is your D. Now similarly, the change in load was 100 kilowatt or zero point 0.1 megawatt divided by MVA base is 2 MVA. So I'll get it as 0.05 per unit. Now you know that delta F is minus 1 by T delta PL. So there is no speed governor action, right? That's why no R is here. So that will be minus 1 by 0.04 into 0.05. It is 1 point minus 1.25 hertz, because this was in per unit megawatt, this was per unit megawatt per hertz. So per unit megawatt will cancel out and hertz will come to the numerator. So its unit will be hertz. So steady state will be F naught plus delta F. So 50 minus 1.25, that is 48.75 hertz. Got the unit right. This was per unit megawatt per hertz. This was per unit megawatt. So you'll get this as hertz. That is option A. Now an isolated loop controller generator supplies 500 kilowatt at 50 hertz. It is observed that 50 kilowatt increase in load results in 49.5 system frequency. Find out the system load for an operating frequency of 50.1. So here isolated loop control is there. So it is telling that supplies F naught F. So let's say initially F naught, that is 50 hertz, and it was P1, and P1 is your 500 kilowatt. So 50 kilowatt increase in load. So when the load is increased by 50, P2, that is P2 is 550 kilowatt, then your, let me write this as F1 and F2. So F2 is 49.5 hertz. So it is saying that when the frequency is 50.1 hertz, so what will be the system load? Okay, so so let this be F naught, that is when no load. This is your no load frequency. So I can write F naught minus F. I'm computing this droop, right? So that is 0, or I can directly write delta F by delta P. So for this change, what was delta F? It was zero point 0.5, and what was change in output power? This was 50, right? So this, now when delta F is 50.1 minus 50, that is zero point 0.1 hertz, then delta P will be this slope into the change in frequency. So what will that be? That is minus 10 kilowatt. So the drop in load will be 10 kilowatt. So P3 will be 500 minus 10 means 490 kilowatt. Right. Now, ninth question is, two generators are rated at 775 and 225 kilowatt and operating in parallel, and both generators have same number of poles and same no load speed. So the governor settings of machines are such that they have 3% and 5% rule. So determine kilowatt load shared by generator A and B. So here it is saying that there are two generators. So same no load means they have same no load frequency also, right? Because you see omega is 2 pi f. So this is same means frequency no load is also same. So one is 5%, one is 3%. Let me draw that clearly first. So this is 5% group, or this is 3%. So 5% is 225 kilowatt. So this is 225 kilowatt, and then 3% one is 775 kilowatt, and they have the same no load frequency FNL. So it is saying that now they are operating at some F, and its output is some P1, or this is, let's say, this is PB, this is PA. So how much load is shared by each unit? So similarly, PA plus PB will be total load, which is 500. Now for generator A, so if you observe these two triangles, this small triangle, this triangle, and the outer one. So these are similar triangles. So I can equate their slopes basically. So I can write that as F no load minus F divided by 0, because the power at no load is 0, at F it is PA. So this is F, this will be F, because at F the power is PA. So that is having 3% drop, means when the power is at this PA, so the drop will be 3%, right? So F naught minus 3% drop, so 0.97 F naught, so that is 0 minus 775 kilowatt, right? Similarly for generator B, that is F no load minus F 0 minus PB. So F no load here troop is 5%, so 0.95 F naught divided by 0 minus 225. So from these two equations and this equation, basically PA, PB and F naught are variables. So F no load is only F naught I have taken here. So using these three equations, you can calculate PA, PB and F naught. So by solving this, you will get PA as 425.816 kilowatt and PB as 74.184 kilowatt. Is this fine? So it is showing the by generator B, so it will be 74, means option D. Now same question, I think it is asking that determine steady state speed deviation as percentage of their no load speed for a total load of 500 kilowatt. Okay, so we got PB as 74.184, and from the second equation for B we have seen that F naught minus 0.95 F naught divided by 225, right? Divided by 0 minus 225. So from here I can say that delta F by F naught is 0.05 divided by 225 into pp, that is 74.184. So that will give me as 0.016485. So steady state speed deviation. So you know speed speed deviation is same as frequency deviation, right? So delta n by delta n naught is same as delta f by f naught. So that is 1.6485%. So that is your option A. Okay, so this brings to the end of our discussion. So if you have any doubts, you can ask, otherwise, we may close the session.